Chapter 7, Section 3, Rotations. This section is kind of a difficult one to maybe see just on a screen what I'm talking about. So this is probably one that if you miss this day, you're probably going to have some questions about it. But you can still go ahead and watch this and get a general idea, and then I can kind of show you. It's a lot of things that I need to like point at and show you, and so it might be a little bit difficult on here. If you can figure it out though, that's great. A rotation is a transformation in which a figure is turned about a fixed point called the center of rotation. A rotation is an isometry, which remember means that all of the angles are going to stay the same, all of the side lengths are going to stay the same. Whatever we rotate is going to be congruent to the original shape that we started with. Rays drawn from the center of rotation to a point and its image form an angle called the angle of rotation. This first example says a quadrilateral has vertices P at 3, -1, Q at 4, 0, R at 4, 3, and S at 2, 4. Rotate PQRS 180 degrees counterclockwise about 0, 0, and name the coordinates of the new vertices. So counterclockwise, if you think about a clock, we start at the top and we go in a circle to the right. Counterclockwise means we're going to start at the top and we're going to go work our way to the left in a circle. When I say counterclockwise about 0, 0, that means that the center of rotation is going to be at the origin. 180 degrees means that from any point through the origin needs to form a 180 degree line or straight line. Notice, I've just kind of gone ahead and grouped this here. Notice what's happened is I've taken my original point, P at 3, -1. I've drawn a straight line through the center of rotation, which was 0, 0. And notice that I've placed P prime, or where I've moved P2 is -3, +1. That is the same distance from the center of rotation, which is the origin. And if I drew a line from each image and pre-image, notice that all of them are forming 180 degree lines through the point 0, 0, the center of rotation. The new points are -2, -4, -4, -3, -4, 0, and -3, 1. This one says triangle RST has coordinates at R at -2, 3, S at 0, 4, and T at 3, 1. If triangle RST is rotated 90 degrees clockwise about the origin, what are the coordinates of the new vertices? What needs to happen here is, remember it's an isometry, so everything's going to stay the same length. All the sides are going to stay the same length, and all of the angles are going to stay the same size. What needs to happen here, though, is clockwise, first of all. So we're going to the right, kind of. We go clockwise about the origin, so I need to be able to draw a line from each point to the origin and then out to their corresponding point that's been the image of the original, and that needs to form a 90 degree angle at the origin. So if I take this point at 0, 4, and I draw a line from there to the origin, and then from the origin out to 4 on the x-axis. Notice both of those lines are equidistant from the origin, and it's forming a 90 degree angle. So I can go ahead and I know that that's going to be my S prime. I can kind of fill in my other pieces as necessary. And then these are my new points. All of these, from the image to the pre-image, form 90 degree angles. I have a point at 3, 2, a point at 4, 0, and a point at 1, -3. Like I said, this is kind of difficult to show you on this screen. I feel like I'm not doing a very good job of explaining this right now because it's really hard to show you without being able to kind of point and talk about how we know that. So like I said, probably not the best lesson to learn off of this video. So if you missed, come see me, please. The theorem from page 414 says if lines K and M intersect at point P, then a reflection in K followed by a reflection in M is a rotation about P. The angle of rotation is 2x, where x is the measure of the acute or right angle P. An illustration of this would be we have triangle JKL is reflected in line K to produce triangle J prime, K prime, L prime. This triangle is then reflected in the line M to produce triangle J double prime, K double prime, L double prime. Describe the transformation that maps triangle JKL onto triangle J double prime, K double prime, L double prime. So if you notice in this illustration, we have the original triangle JLK or JKL, which is the blue triangle. The first transformation is that it's reflected over line K to give us J prime, K prime, L prime. Then we can kind of forget about the original for a minute. Then that J prime, K prime, L prime has been reflected over line M to give us J double prime, K double prime, L double prime. The relationship between the original triangle JKL and this very last triangle that we've transformed, J double prime, K double prime, L double prime, is actually going to be a rotation. And we can find the angle of rotation. If you notice, it tells us that line K and line M intersect at point P to form a 45-degree angle. So the theorem that we just talked about says that we can take that acute angle that's 45 degrees and we can multiply it by 2 to give us, to tell us that that transformation from the original triangle JKL to the last triangle J double prime, K double prime, L double prime is going to be 90 degrees, and it would be 90 degrees clockwise. That is important because counterclockwise we would actually be over, it would be completely different ordered pairs and everything. So make sure that you tell me clockwise or counterclockwise. A figure in a plane has rotational symmetry if the figure can be mapped onto itself by a rotation of 180 degrees or less. Which figures have rotational symmetry? For those that do, describe the rotations that map the figure onto itself. If you look at A, it's a kite. The only time that it's going to be back to, if I took this shape and I turned it, the only time that it's going to be back looking and mapped onto itself is when I've done a full 360-degree turn. So because that is the case, it does not have any rotational symmetry. If you look at B, though, it's an equilateral triangle. If I took this triangle and I rotated it, it would actually map onto itself in a full 360-degree turn. It would map onto itself 3 different times. Because that is the case in a full turn that's 360 degrees, it would map onto itself 3 times, and those 3 times that it would map onto itself are equal distant apart, or an equal rotation from each other. So this does have rotational symmetry, and what I do to find the angle of rotation is I take 360 and I divide it by 3 because that's how many total turns, total times it would map onto itself in a complete turn. So it can be rotated onto itself by a clockwise or counterclockwise rotation of 120 degrees in about its center. The reason why, if I do 360 divided by 3, it's 120. The reason why it can't be 240 is because that's not less than 180 degrees. The next example says, explain how the design can be mapped onto itself by a rotation. The first answer is already up there. If you notice, we have 3 different squares here. However, each time I rotate this 90 degrees, it will map onto itself. Remember, the definition of rotational symmetry is that it has to have a degree of 180 degrees or less. So the 2 degrees can be rotated onto itself clockwise or counterclockwise by a rotation of 90 degrees and 180 degrees. And then the second example, if you notice, we have kind of this funky shape. The only time that it's going to map onto itself is after half of a turn. Half of a turn measures 180 degrees, so it can be rotated onto itself by a clockwise or counterclockwise rotation of 180 degrees. It doesn't matter if I'm going clockwise or counterclockwise. Either way, it's going to map onto itself. Today's assignment is on page 416. It's numbers 13 through 19, and then 26 through 38 even.